Hello, this is my final project on Fast Speech 2. It is a text-to-speech algorithm. So essentially you give it a sentence and it produces audio. In order to do this, we use Mel spectrograms and phoneme embeddings of text. So this phonemes will be mapped and learned to convert to Mel spectrograms, and then we transform that into audio. So Mel spectrograms are actually fast Fourier transforms of audio waves across a window of time, and then we apply a Mel filter bank in order to get the Mel spectrogram. And phonemes are vocalizations and how we say the words. And so we embed the words into these phonemes, which then we can learn how to map to our Mel spectrogram. And we use this in Fast Speech 2 with 3 different hyperparameters. There's energy, duration, and pitch. And this will define the characteristics of the audio that you produce. So how fast the person is speaking, how slowly, how much space is in between the words, how high or low is their voice. And so the Fast Speech 2 algorithm is actually a continuation of the Fast Speech algorithm in paper. And that one, Fast Speech, was looking to remove the auto-regressive transformers at the beginning of the networks because it was back-propagating the errors and encouraging repeating words and skipping words. And so they introduced the feed-forward transformer, which is described in the green block at the bottom. So this feed-forward transformer is essentially a attention layer with a convolutional layer. And this embedding of the phoneme actually is a different dimension than your Mel spectrogram. And in order to compensate and to sort of upsample this hidden phoneme layer to your hidden Mel spectrogram, they added a deeper network of just 2 convolutional layers with a linear layer. And that way they moved to Fast Speech 2. So they left the encoder as the feed-forward transformer, and then they implemented a variance adapter. So this is going to be helping you move from that hidden phoneme dimension to the Mel spectrogram hidden embedding. And the variance adapter has 3 hyperparameters: the energy, pitch, and duration. And each one of these is actually trained on a deeper network. Again, it's the 2 convolutional layers with a linear layer, and then there's dropouts in between. And the implementation that I used for this particular Fast Speech 2 was on a same named Fast Speech 2 GitHub repository. I chose this because it is open and it has well-written objects. So I could go ahead and change mostly the postnet. So the postnet on this implementation was set to convolutional networks. And in the paper they described a rather large residual network. So the decoder was described as 30 blocks of 64 skip channels, which is rather large. But I added in the functionality of this residual network for postnet, and you can designate the number of blocks that you want and then how many skip channels. Some of the other drawbacks to this particular implementation, there was a lot of command line instructions, and you needed to manually download files and then decompress them and make sure that they were all in the proper directories. I wanted to streamline that and make sure that this implementation can be easily followed with just a simple Python script. There were some issues with the requirements text file as well. It seems like some of the packages have had major updates, and so there were some dependency issues, and I re-engineered the requirements text file to go ahead and solve the environment so we can go ahead and implement the model. And then after just hour or two of runtime on the training, you do get out a fairly good model. And you can look at your losses through TensorBoard. A TensorBoard will not only give you, total loss, but you can also look at the loss for your hyperparameters, for your mil spectrograms as well. And then you also get out audio in your validation and training. And then you can use your model to synthesize a new sentence. And so here's two examples.
He was, I take it, the most perfect reasoning and observing machine that the world has seen. He was, I take it, the most perfect reasoning and observing machine that the world has seen.
So there might not be some large differences in between these particular audio files. However, there is some hesitation between the words, some different emphases, and then that is what the models learned were these hyperparameters, the energy and the pitch. And I want to look at the script file, walk through that just a little bit that I created. So initially, we set up our requirements, making sure I have an actual graphics card that I can run this on. And then you do need to set a home directory. One of these path file configurations in here does operate on an absolute path rather than just a relative. But then you do need to download your corpus and then decompress all of that. And there are a couple of other files on here that you need to just decompress. And then config files. So the config files are within subdirectories of subdirectories because this particular implementation does allow you to use multiple different corpus if you so choose. I wanted a little bit easier access to these config files so we can follow along just a little bit better. And in these config files, we just read out the file, and it is essentially a dictionary. So here I gave an example. You can set your postnet and then how many convolutions you want. We want 5. And then you can decide if you want the ResNet or if you want like just the convolutional net. And we read that back into our file. We also have some pre-processing parameters. Most of this you will not need to reset. Most of the concerns here are just going to be the pathing. So this is where your home directory comes into play. And then we also do need the sample rate from here in order to do some synthesis later on. And then the training parameters for your config files. I did have to change the batch size to a smaller size in order to run on my local computer. I do want to point out that you can also have the adaptive optimizer. So this is going to be your learning rate steps. And you can also set, how long, how many steps you want to train for, and then your logging steps as well. Here is some alignments. So for this portion of this, he does recommend that you just download the shared files of alignments. But there is a possibility as well for you to follow along with this different program in order to align the particular corpus that you're using. But this one is much simpler. And just make sure that your WAV files are within this particular file path. And then here we pre-process some data. This runs on the CPU, so this will take some time. On my local computer, it was about half an hour. And then this is the meat and potatoes of training your model. This part will take the longest, 2-3 hours on my local computer. And then again, this is your TensorBoard. This will give a lot of different loss values, and then also your mil spectrograms, and then audio. Now the fun part is you can add in your own text. So then we synthesize, and you can also change the pitch, energy, and duration to make the audio sound a little bit different.
Tap your text here.
And then in just a couple seconds, you get your audio back out.
Check your text here.
So you can see how the duration stretches out the words there. And you can play around with some of these to get a little bit more of an intuitive feeling for how the Fast Speech 2 process actually works. And you can also do this for batches. So you have multiple sentences and you can create, a whole paragraph if you would like. And then I would like to look at some TensorBoard output here. So here's some loss values and then validation. Validation is the less noisy version. So the validation loss is actually doing better than some of the training. So the images I find some of the most interesting, actually. You can see the synthesized version looks really clean compared to the ground truth. This may be why it sounds a bit tinny, but you can also see this ground truth, it does have that higher energy in wavelets where we haven't quite gotten there with our models. So there is room for improvement on our specific details here. And then the audio. So it does describe, which step it pulled this audio from. And this is one where it's supposed to sound like.
Bates was at once captured in Norfolk Street, Strand.
And then here's the synthesized version.
Bates was at once captured in Norfolk Street, Strand.
And then here's the other model.
Bates was at once captured in Norfolk Street, Strand.
And that's what it was supposed to sound like. And then
Bates was at once captured in Norfolk Street, Strand.
So clearly these models do have some room for improvement. I did run quite a few other different iterations on learning rates and changing how many attention heads were on the transformer. If you do increase the attention heads, it increases the training time drastically, but it actually does improve the output audio, the synthesized audio, drastically as well. So I do encourage you to play around with some of the attention head configurations. And that is it for my Fast Speech 2 text-to-speech algorithm and implementation. Thank you.